Hello students, and welcome to the new module, and that is about the combinational circuits. In this module we are going to discuss and design a lot of combinational circuits. So in the first video we are going to talk about the circuits themselves. So in this video we are going to discuss that there are two types of digital systems and how can we describe the first type, and that is combinational circuits. We are going to talk about Boolean algebra and the truth table, which are useful in describing the combinational circuits. So let us get started. So we had already discussed that there are two types of digital circuits. The first one is combinational circuits and the second one is sequential circuits. When we talk about combinational circuits, we had discussed that these are the circuits without memory and they are made of logic gates. Here, the current value of input is going to define the current value of output. There is no role of the previous outputs or any stored memory values in calculation of the current output. These circuits are mainly used for performing the arithmetic operations like addition, multiplication, shifting, comparing, and all these things. So we had also seen this block diagram that the current inputs will decide the current output. There is no feedback at all. Combinational circuits are made of logic gates. Logic gates are like AND or NOT, NAND, NOR, XOR, XNOR, and there can be a few more logic gates in the literature. We describe these arithmetic functions using these logic gates, and that is what make the combinational circuit. Any Boolean function that we have can be described by the following three methods: using Boolean algebra, truth table, and logic diagram. Let us discuss these three methods in detail. So when we talk about the Boolean algebra, it is having Boolean expressions and Boolean operations. The Boolean expressions or these algebraic expressions, they show the operation of logic circuit for each input variable. We are going to have few input variables and we are going to calculate the output variable expressions. So these expressions are basically describing the relation between these inputs and outputs. There are two types of condition that we have: true and false. True is represented by 1 and false is represented by 0. And or invert. These three are the only possible operations in Boolean algebra. Every other operation is made by the combination of these three. Like if I want to make NAND, that is AND plus NOT. If I want to make NOR, that is OR plus NOT. So these three are the basic gates. There is another thing called universal gates, and NAND and NOR are the universal gate. So in Boolean algebra, we are going to get the relations in the form of these Boolean expressions. The second type which we have is the truth table. This method can also describe the Boolean function of a combinational circuit. So here we use a tabular method for representing the same sort of relation. The values will be represented as true, false or 1, 0, and truth table can be used to obtain further Boolean expressions. So here we have one truth table of two inputs. When we have two inputs, then we can generate 2 raised to power 2, that is 4 input cases. We can observe here that in the output column, 3 values are 0 and 1 is 1. That means the output is false for 3 input cases and output is true for only 1 input case. Let us see an example where we are trying to obtain the Boolean expressions from a truth table. So here I have three inputs, x1, x2, x3. So if I have three input, I am going to have 2 raised to power 3. That means 8 input cases. And we can observe in this truth table that 4 outputs are 1 and 4 outputs are 0. How do we obtain the expression from such truth table? So first of all, what I have done here, that I have segregated the zeros on one side and ones on one side in my output side. We may not need it, but this is just for the simple explanation. Now let us understand how do we obtain these expressions from this table. So here I have three inputs, x1, x2 and x3. When I am talking about 0 cases, here we call them as product of sum form of the Boolean expression. We are going to take the value of input variable, and if it is 0, then we will take the variable as it is, and if it is 1, then we will complement the variable. So here in the first case we have x1 and we are going to take a sum between every value, x1 plus x2 plus x3. So that becomes my first sum term, this one. When I go to the next one, I find x1 plus x2 bar. Here it is 1, so I am going to complement x2. x1 plus x2 bar plus x3, and that is my second sum term. Similarly, the third one will be x1 bar plus x2 plus x3, which is here. And the fourth one will be x1 bar plus x2 bar plus x3, and that is my fourth sum term. And if I take product of all of them, that is my complete expression for y. There is another way of representing the Boolean expressions which is more popular, and that is sum of products. In this, we take the exactly opposite logic. Okay, that means we are going to count the ones. Now we are not even going to look at the zeros. So we have 4 ones. Every term where the output is 1 is going to be called as a product term. That means between every two variable I am going to have a dot. That means product. And the variables, if it is 0, it will be taken with a complement, and if it is 1, it will be taken as it is. So the first product term will be x1 bar dot x2 bar dot x3. So here we have x1 bar dot x2 bar dot x3. Similarly, the second one will be x1 bar dot x2 dot x3. So this is here x1 bar dot x2 dot x3. Similarly, the third one is x1 dot x2 bar dot x3, and the last one will be x1 dot x2 dot x3. We are going to share a PDF with you in the resource section where you will have more examples to practice that how can you convert a truth table into a Boolean expression. So now we know about the truth table method. Once we have the Boolean expressions, then we can transform these Boolean expressions into the logic diagram, and that is the third way of representing your combinational circuits. So if you can see here that we are having x, y and z. Here are two NOT gates, so we get x bar, y bar, and then there is AND gate. So I get x bar dot y bar dot z. So this is the product term, and which is from here. So if I am given a Boolean expression like this, I can transform this into this. Then I transform this into this one. Then the next one. Then the next one. So here and here. And finally there is a sum between all four. So I take one OR gate. Another example is here. X dot y AND gate, y dot z AND gate, and x dot z another AND gate, and in between three product terms there are sum, that means OR gate of 3. We are going to share one more worksheet with you where you will have more examples related to converting Boolean expressions into the logic diagrams. So students, now we know a little bit about combinational circuits and how can we describe them. The next task is how do we design them. We'll talk about that in our next video. Keep learning. Thank you.